Hi guys, so today we're going to look some more at radians, and specifically what we're going to look at today is how to graph them and how to find reference angles. It's very similar to what we did with angles, but it's a little bit tougher just because of the fraction aspect of it. And then we're also going to look at some applications of it using something called angular velocity. So the first thing we're going to look at is this little chart that you guys have. You either can redraw this yourself or just glue it into your notebook. But what we're going to do is take each angle that's on the given side and we're going to graph it, and we're also going to find the reference angle. And this just kind of gives us a step-by-step process to hopefully make this a little bit easier. So the first thing we're going to do is we're going to look and see, is that angle between 0 and 2 pi? Because if it's not, it's going to be a lot easier for us to find a coterminal angle. So 4 pi over 9, that is between 0 and 2 pi, so we don't need to worry about that first column. Now what I'm going to do is I'm going to go ahead and write on my graph, I'm going to write pi and 2 pi with a common denominator as my given angle, just to make these values a little bit easier to see. So instead of writing pi, I'm going to write that as 9 pi over 9. And instead of writing 2 pi, I'm going to write that as 18 pi over 9. Because that common denominator is going to make it a little bit easier for me to figure out where 4 pi over 9 is going to fall. So in that next column, it asks me to figure out, based on those two numbers I just found, is 4 pi over 9 going to be closer to 0, to 9 pi over 9, or to 18 pi over 9? And we know 4 pi over 9 is going to be closer to 0. So that helps us figure out what quadrant should this go in. And I'm a little bit out of space here because it's hard to write with a stylus. But I know this column is going to be here, because 4 pi over 9 is closer to 0 than it is to 9 pi over 9. It's 4 away as opposed to 5 away. So this is in the first quadrant. So I sketched my terminal side. So if I were to actually graph this angle, it would just be like that. Now the last question, it says how close. So how close is it to the horizontal line? How close is 4 pi over 9 to 0? And in this case it is 4 pi over 9 away, which means 4 pi over 9, that's my reference angle. So we're going to try another, negative 5 pi over 8. Now for these negative angles, it's up to you if you want to find a coterminal angle. For some of you guys, that will make it easier. For some of you guys, though, you probably could figure this out based on where it is. So I'm going to not find a coterminal angle for this one, just to see if we can still work on this negatively. So if it's a negative 5 pi over 8, I'm going to label pi and 2 pi, except I'm going to go backwards. So I'm going to label this as a negative pi, which is going to be negative 8 pi over 8. And then if I were to go all the way around a full circle, that would be a negative 16 pi over 8. And I know negative angles, I'd be moving this direction. So now I just have to figure out which one is it closest to in that negative direction, and I'm going to sketch my terminal side. So I know this angle is closest to pi, so it's still going to fall in the third quadrant, and I've traveled in the negative direction 5 pi over 8. So that's what my angle would look like. And then I just need to find how much is that in-between area, and that's going to be my reference angle. So in this case, I know it's a distance to pi to the straight line, so that straight line would be 8 pi over 8. But I went to 5 pi over 8 for my angle, which makes my reference angle 3 pi over 8. Now, while it would be negative in that direction, remember our reference angle is always positive. So the reference angle here would be 3 pi over 8. Alright, so the next one, 19 pi over 6, that one is more than 2 pi, so I need to find a coterminal angle here. So in order to find a coterminal angle, I'm going to subtract 2 pi. But I need a common denominator, so that common denominator I need to multiply both sides by 6. So that means I'm really subtracting 12 pi over 6 to get that value of 7 pi over 6. So my coterminal angle is 7 pi over 6. Now I'm going to graph 0 and 2 pi. I'm going to plot those with that common denominator. So I'll do 6 pi over 6 and 12 pi over 6. And now I'm going to sketch the terminal side by figuring out which one's it closest to. Well, 7 pi over 6 is closer to 6 pi over 6 than it is to 12 pi over 6. That means 7 pi over 6 is going to fall in the third quadrant. If I were to draw this angle and not just sketch the terminal side, I would have to do the full circle and then end at that point. But since I'm worried more about the reference angle right now, I'm going to leave that off. So my reference angle is going to be this in-between part. I know it's 6 pi over 6 to that top line. And I know I graphed 7 pi over 6. So the difference between those two when I subtract them is just a difference of pi over 6, which makes that my reference angle. Alright, if you want, go ahead and pause the video and try the next one on your own. And I'm going to show you guys the answer to that one. Alright, so if you work that one on your own, you should have gotten a reference angle of 3 pi over 3, because this radian value is going to fall in the fourth quadrant. My 1 pi would be 13 pi over 3, my 2 pi would be 26 pi over 3, and I know that's going to be closest to 2 pi, which is 26 pi over 13. And that difference between them, 26 pi over 13 minus 23 pi over 13, gave me a difference of 3 pi over 13. Alright, now this last one on there, a negative 11 pi over 3, I need to find a coterminal angle at least one time, because this is even bigger than a negative 2 pi. So I'm going to add 6 pi over 3, and that gives me a negative 5 pi over 3. So if I were to move in the negative direction, this is 3 pi over 3 negative if I'm going this way, or this would be 6 pi over 3. Going in the negative direction, it's going to be closer to 6 pi over 3, so that means if I'm moving in this direction, I'm going to end in the first quadrant. So the terminal side of my angle is going to be in the first quadrant, which means the reference angle is simply the value between the x-axis and the terminal side, which in this case is just pi over 3. Alright, so that's sketching radian values and finding reference angles. Again, if you draw the picture, it's helpful, and it's mostly just working with fractions. The last thing we're going to look at is just an application, and that is something called, we're going to use angular velocity and regular old linear velocity. Angular velocity is this little symbol that's up here at the front. That is omega, which is a Greek letter, but it's going to be our symbol for angular velocity. And angular velocity we're going to look at very similar to, we know that distance is equal to rate times time. So my rate here is the omega. I know rate then would be equal to distance divided by time. That's essentially what I have here on this formula, except my distance, you'll notice, isn't d, it's theta. So what we're looking at, because it's angular, we're looking at the distance traveled in terms of radius, or radians, in a circle. So this theta value here, that is the radians traveled in that amount of time. And you'll see that in questions listed mostly as revolutions. Okay, revolutions. Now about those revolutions though, if you remember the amount of radians traveled around a full circle, if I make one revolution around a circle, I've traveled 2 pi radians. So what I would do is I would take the number of revolutions and I would multiply that by 2 pi. That's what that theta value is going to stand for. So if we look at this first example down here, it says a belt runs a pulley of radius 6 centimeters at 80 revolutions per minute. I want to find the angular velocity of the pulley in radians per second. So I want to know how fast that pulley is going, the velocity of it, in that distance around that circle. So again, my distance equal to rate times time, which means my rate here, my rate is going to equal the distance traveled divided by time. Well, I know my time is per minute. That's what it gives me. So in 1 minute, I traveled 80 revolutions. 80 revolutions is a distance of 160 pi. So that means that I've gone 160 pi radians in 1 minute. All I need to do now is just convert this to radians per second, which means I can multiply by 1 minute over 60 seconds. My minutes cancel, and I'm left with 160 pi over 60 radians per second. Simplify that, that's 16 over 6, which reduces to 8 pi over 3. So that would be my angular velocity there. So 8 pi over 3 radians per second. That's how many circles or how far that distance is per second, 8 pi over 3. The last one on here is linear velocity. So what linear velocity is going to do is it's still going to be traveling in a circle, but it's going to take a specific point on that circle. So this is when the radius is actually going to factor in. So in order to find angular velocity, I'm basically going to do the radius times the distance traveled. Okay, so the theta value is still going to be my revolutions times 2 pi, because that's the total distance in radians traveled. So to get angular velocity, which is part B, it says to find the linear velocity in centimeters per second. So the only difference here for part B is that I don't just need 160 pi, I need 160 pi times that 6 centimeters. And then I see how long it took me to do that. It once again per second, so it took me 60 seconds because it was 1 minute. And then I just do the math to simplify. And that should simplify just to 16 pi inches per second. So my linear velocity then is 16 pi inches per second. Now this last little box on there is really just a way for us to check to make sure these values make sense. What that tells us is that linear velocity is equal to omega times r, which basically means my linear velocity should equal the radius of the point that I'm looking at times the angular velocity. So we can double check to make sure our answer makes sense. This means that the linear velocity, so 16 pi, should equal the radius of the point I'm looking at, which is 6, times my angular velocity, which worked out to be 8 pi over 3. And if we work that out, I do get 16 pi is equal to 16 pi.